So let's remind ourselves of some derivative rules. How does this go any higher? Nope, it sure doesn't. Okay, well, that's fine. Yeah, okay. Probably, yeah, let's just write them down real quick. So if your function is x to some power, then its derivative is that power times x to the 1 less power. Powerful, good time. We also have the product rule. If you're taking the derivative of a product, I always think of it as the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. And this actually is true for a product of any number of things. So what I mean by that is if you have like a product of 3 things, it's always the derivative of one piece times the rest of the pieces. So for example, if I was going to take the derivative of the product of the functions f, g, and h, it would be f prime times g times h plus f times g prime times h plus f times g times h prime. And you could extend that to any number of things. So if you had like a derivative of a product of 4 things, there would be 4 pieces. F, the derivative of one piece times the other 3, plus the derivative of the next piece times the other 3, and so on and so on. We have the quotient rule. If you want to take the derivative of f of x divided by g of x, it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Now, I might have written this in a slightly different way than you're used to seeing it. Most people probably write it as f prime g minus fg prime all over g squared. But the way I say it in my head, and it just sounds better, is the bottom times the derivative of the top instead of the derivative of the top times the bottom. But still doesn't matter. It doesn't matter what order you multiply things in. And then lastly, we have the chain rule. So if I want to take the derivative of f of g of x, it's going to be the derivative of the outer function, leave the inside function alone, multiply by the derivative of the inside. So those are general rules we should be aware of. And normally I'm not so much of a just write the rules down kind of guy, but I thought it might be good just to see this as a refresher. We're definitely going to do some examples in just a second here. Also, let me ask the people on Zoom. I feel like the picture looks very dark. Is that just me or is that you all as well? Maybe it's just my screen. Yeah, maybe if I just make my screen lighter there. Okay, yeah. It's probably just me. I'll try to keep things visible as long as possible, but I do kind of move somewhat quickly and have to turn the page over. Also, I will just remind you, the video is going to be posted later. If you need to come back and look at anything, the notes will also be posted. So if you missed something and you need to see it later, you're welcome. You're welcome to ask me, like, James, can you wait just a second? But eventually I will move along and you can always look at the posted notes later. So let's look at some examples. Actually, I should say, before we do some examples, one other list of things I would like to remind you of are the derivatives of trig functions. I imagine that's something everyone covered in 16A, derivatives of trig functions. Okay, so I feel like sometimes it didn't always used to be part of the syllabus, but I think that's not true anymore. So let's remind ourselves of them really quick. So some other notation for derivatives. So the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. I encourage you to write them in this order. It's kind of the usual pattern for writing the trig functions: sine, cosine, and then tangent. It also helps me remember that sine divided by cosine is equal to tangent. And then to the right, we write the reciprocal functions. The reciprocal of sine is cosecant. The derivative of cosecant of x is negative cosecant of x times cotangent of x. Reciprocal of cosine is secant, and the derivative of secant of x is secant of x times tangent of x. And the reciprocal of tangent is cotangent, and the derivative of cotangent of x is negative cosecant squared of x. Couple patterns to remember about these trig derivatives. Each cofunction has a negative derivative. And when I say cofunction, I mean cosine, cotangent, and cosecant. Those are all cofunctions, and their derivatives are negative. That's something it's useful, especially when you start doing antiderivatives, as we're going to be doing this quarter. It kind of helps you figure out what's going to be what. All right, so those are really, like, as far as I'm concerned, the major things we need to remember from last quarter. Derivatives of trig functions and the derivative rules. Those are all going to kind of pop up as we move forward. So let me have you guys do a problem. Why don't you try this one? Find the derivative of that. 5x to the 7th plus 1 over x to the 9th plus x squared sine of x. And yeah, that is a 9. I should also clarify, if anything ever looks unclear, I won't be offended if you say something. I know my writing is like okay-ish. So if you're not sure if something says, just ask. So give that one a shot. People at home on Zoom too, you should give it a shot as well. Problem with being stuck up here is I don't want to walk back. But I feel like I should stay up here. So I think, unfortunately, this quarter it's going to be less me asking you to do things as much as I would like to, and more me showing. I will try to move away from that as we go on, but at least in the beginning, I feel like it's a lot of me showing. That said, ask questions if you've got them. Also, oh, I know what else I want to say. Sorry, quick aside. If you have things you want to see, like on Thursday or next Tuesday or whenever, you can definitely send me, like, hey, James, you covered this class. I really like to cover. I'm usually keeping track of what your professors are doing, but also, like, if there's something really like, we did this, it was weird, confusing, or I want to know more about it, let me know. You can either, the best thing to do would actually be to write a discussion in Canvas, because then other people can see it as well. If you're comfortable with that, I understand maybe not wanting to do that. You're also welcome to send me an email and I'll be like, oh yeah, totally. But yeah, if you let me know about something, I'm really more than happy to try to make sure we cover it in class. So to take the derivative of this, I'm actually going to rewrite it first. I'm going to rewrite it as the derivative of 5x to the 7th plus x to the negative 9th plus x squared times sine of x. You don't really need these parentheses around it. It's nice, but not required. The derivative of 5x to the 7th is going to be 35x to the 6th. The derivative of x to the negative 9th is going to be minus 9 times x to the negative 10th. And the derivative of this, we're going to use the product rule. So it's going to be the derivative of x squared times sine of x plus x squared times the derivative of sine of x. Questions, comments? All right, I'm gonna stop asking. It's a terrible habit. Like, just be like, so you guys have any questions? If you have questions, you'll ask them, I assume. I'm gonna keep going, but really, like, I want to give you the opportunity to ask questions, but also I should just be like, here we go. But really, like, you should stop me if you have a question or something you want to ask about. Or if I made a mistake, because I definitely make mistakes. Not on purpose most of the time. How did I get 9x to the 10th? So it's not quite 9x to the 10th, it's negative 9x to the negative 10th. So what we're doing there is we're using the power rule. So real quick off to the side here. The derivative of x to the negative 9th. So the power comes down, we get negative 9 times x to the negative 9 minus 1. And negative 9 minus 1 is going to be less, which is going to be negative 10. That's negative 9 times x to the negative 10th. And I wrote it here as minus 9 times x to the negative 10th. I could have instead written it as 35x to the 6th plus negative 9 times x to the negative 10th. But I didn't want to write all that. But you certainly could write all that if you wanted to. So yeah, so when you take a derivative of x to a negative power, the power gets more negative because you're subtracting one from it. Let's look at a couple more examples of derivatives, and then we're going to move on to talk about exponential functions. Let's see. Let's do this one. Let's find the. So there's lots of ways to write functions and write how to take the derivative. One way to do it, the notation I mostly like to use, is the derivative with respect to x of the thing you're taking the derivative of. But an equally valid way to do this is to say, like, your function is the thing, and then ask what the derivative of that is. So for example, my function might be something like, I don't know, x cubed plus cosine of x over x minus tangent of x. And I could say take the derivative of that, or I could say my function is x cubed plus cosine of x divided by x minus tangent of x, and ask what's the derivative. Both of these ways of writing it are getting at the same thing. It's just different notation. A lot of people prefer to write this, mostly because it's the least amount of writing. Right? Oh, take the derivative of the thing. All right. So let's take the derivative of the thing. Quotient rule, right? We have a fraction, we have a quotient. It's going to be the bottom times the derivative of the top. The derivative of the top is going to be 3x squared plus negative sine. So I'm going to write minus sine of x minus the top times the derivative of the bottom. The derivative of x is 1. The derivative tangent of x is secant squared of x. A little close the room there. All divided by x minus tangent x quantity squared. There is no good reason. That's not true. As the problem is asked, there is no good reason to simplify this. Right? You shouldn't multiply at the top. You shouldn't really do any of that. The exception being if you're asked to maybe find a critical value. So if someone said, find the critical values of this function, then you would want to set it equal to 0 and solve, and then you would probably simplify it. Another good reason to simplify a derivative is if you have to take the second derivative. Taking the derivative of this would be terrible. It's still going to be terrible if you simplify it, but it'd be a little bit less terrible. So simplification is useful, but not necessary. As far as web work is concerned, web work will take pretty much anything as long as it's right. So if simplifying it is really terrible, you can just type the whole thing in. Now, sometimes typing the whole thing in is also really terrible, but it's not usually as terrible as simplifying it. If you're in Professor Burke's class, I strongly encourage you to, I know you only have to do like half of the homework assignment to get full credit. In general, I encourage you to do all of the homework assignment just as a rule. It's good practice, especially this first assignment. It's mostly just making sure you're competent with all the ways you can put things into web work. So I really definitely encourage all of you to do all the problems on this first web work assignment, because it's just helping you make sure you're able to do things better later. But yes, you should do all the homework anyway. I know it's easy for me to say I don't have to do it, but it's good practice. The only way you're going to get better at the math is by doing the practicing. Let's look at one more example. Let's say we want to take the derivative of something like, let's do that. Let's do cotangent to the fourth of x to the sixth plus sine of 3x. Let's see, shouldn't it be? Oh, cool. Looks like someone answered their own question. Great. Yeah. Great. Someone asked if it should be something else on top, and then they realized that it was switched around. So this definitely looks like a chain rule kind of problem, right? I've got a function of a function. In fact, when I have a trig function to a power, I really want to rewrite it as that trig function, cotangent of x to the sixth plus sine of 3x, all raised to the fourth power. Because when I'm thinking I have to use the chain rule, I really need to identify what the outermost function is, because we kind of work from the outside in. So when I see cotangent of x to the sixth plus sine of 3x all raised to the fourth power, I'm thinking, oh, I have some stuff to the fourth power. And the derivative of x to the fourth is 4x cubed. The derivative of some stuff to the fourth, I made a small error here. Not a huge deal, we're going to fix it. But the error I made that I want to point out is I wrote the derivative of this equals just the function. I forgot to write the derivative, right? These are different things. So I need to be a little bit more careful here. I should be saying I'm taking the derivative of all that. But now I'm going to take the derivative. So I'm no longer going to write the derivative simple. So I'm going to get 4 times my stuff to the third power. My stuff being cotangent of x to the sixth plus sine of 3x. But what do I have to multiply by? I know it's a very general question. Watch, it's a very specific question. What I need to multiply by is the derivative of the stuff. So whenever I'm using the chain rule, I'm thinking, oh, I've got a function of some stuff. And the inside stuff, we always have to multiply by its derivative, which might also require the chain rule again. It's okay. So I'm trying to take the derivative of cotangent of x to the sixth plus sine of 3x. Well, I know the derivative of cotangent of x is negative cosecant squared of x. So the derivative of cotangent of some new stuff is going to be negative cosecant squared of that new stuff. Times the derivative of that new stuff. These problems can get a little bit lengthy. Let's see, the derivative of x to the sixth is 6x to the fifth. The derivative of sine of 3x, what's the derivative of sine of 3x? What's the derivative of sine? Right, now I should be, so this is a very common laziness that almost all of us do, is we say sine, we mean sine of x, right? The derivative of sine of x is cosine of x. You can't really have sine without something to take sine of. Kind of like you can't have a square root without like having something you're taking the square root of. So the derivative of sine of x is cosine of x. The derivative of sine of 3x is cosine of 3x times the derivative of 3x. Because again, the chain rule. So here's 4 times my stuff cubed, and here is the derivative of all that stuff. That's kind of a complicated example. Maybe I should start off with a slightly easier one. Let me give you guys an easier one to kind of try out for yourselves, just to remind yourselves of the chain rule, because I will promise you all these rules are going to be definitely things we're using this quarter. So why don't you all try the following? Find the derivative of, let's make it like that. Let's do sine of x plus 2x to the 5th, all raised to the 9th power. Find the derivative of that. And what I would encourage you to say to yourselves is you have some stuff to the 9th power, and you're trying to take the derivative of something to the 9th power. Yeah. Yeah. So yeah, let's go over it. So when I look at this, I see, as I said before, some stuff to the 9th power. And what I'm really doing is I'm thinking about replacing the stuff with an x, kind of. So I know the derivative of x to the 9th is 9x to the 8th. The derivative of some stuff to the 9th is going to be 9 times my stuff to the 8th power times, well, I said stuff. If I said stuff, what do I have to multiply by? Almost, not stuff, but the derivative of the stuff. I use the word, like, you're gonna hear the word stuff like a million times in this class, because I say it a lot. Because stuff is like the most, sometimes I'll say junk, sometimes I'll say trash, sometimes I'll say jazz, but stuff, right? Like we have some stuff to a power. And the derivative of some stuff to a power is that power times your stuff to the 1 less power times the derivative of your stuff. And then the stuff is sine of x plus 2x to the 5th. Now I didn't make it super duper clear, but since there isn't parentheses around all this, it's implied that it's sine of x, right? It's not sine of all of that, it's just sine of x. The derivative of sine of x is cosine of x. The derivative of 2x to the 5th is 10x to the 4th. And now if you look at the way I've written this, it's slightly wrong, because it looks like I've got 9 times all this to the 8th power times cosine of x. And then after that, plus 10x to the 4th. But really, the chain rule says it has to be the outer function derivative, leave the inside alone, and then multiply all of that by the entire derivative. So I need always parentheses around the derivative of my stuff. Otherwise, it's just not going to be quite right. I think we should do a couple. So I will say the chain of all the like derivative rules we have, the chain rule is the one, I don't want to say it's the most important because they're all important, but it's the one that is heavily featured when you start talking about a particular method of integration called U substitution. So the chain rule and U substitution are kind of like I don't have a good analogy, but they go together. They're very related to each other. They're kind of undoing each other. So it's really important that we have a good grasp of the chain rule so that later on when we're talking about use substitution, it actually kind of makes sense. So I think a little more practice is well deserved. So why don't you try finding the derivative of, I'll make it a little bit different, but not that different. Let's do, yeah, I like secant. Secant of x plus x to the 7th, all raised to the 13th power. I know it's a very similar problem, but I think it's worth practicing. And then if you're done with that one, you can try this next one. Functions. About this power mass that walk around the field. Look good, yeah. We'll do one more. All right, let's talk about this first one I wrote. Sorry, I was just trying to think how to say what I want to say. When you're finding the derivative of something, what I would remind you all is that these are just instructions. This ddx here is just something that says take the derivative. And once you take the derivative, you no longer need to write that. I have not actually saw anyone writing that, but just in the past, I've certainly seen a lot of people like keep that thing. So this is just an instruction. Later on, we start talking about taking integrals. It's the same kind of deal. There's going to be an integral symbol, and it's going to mean find the integral. But then once you've done it, you don't write that thing anymore. So take the derivative of this. Okay, I've got some stuff to the 13th power. My derivative is 13 times my stuff to the 12th power. My stuff is secant of x plus x to the 7th. And then I have to multiply, of course, by the derivative of the stuff. The derivative of secant of x is secant of x times tangent of x. The derivative of x to the 7th is 7x to the 6th. That's what she got. Okay. We'll do one more and then one more after that. Here, we don't have some stuff to a power. We have tangent of some stuff. And the derivative tangent of x is secant squared of x. So the derivative tangent of some stuff is going to be secant squared of the stuff times the derivative of the stuff. So secant squared of x to the 5th plus x to the negative 5th plus 6 times the derivative of that stuff, which is 5x to the 4th minus 5x to the negative 6, or you could write plus negative 5x to the negative 6. And then you could write plus 0. I really don't think we need to, though, because plus 0 doesn't change anything. But the derivative of 6 would be 0 because it's just a constant. There was something there. Oh, no, okay. All right, one more I want to throw at you just because it's something that comes up occasionally that people get a little tripped up about. I want to find the derivative of secant of x cubed over 5. Secant and cosecant are a little bit weird when it comes to the chain rule. Because unlike most other functions, when you take the derivative of secant of a thing, or some stuff, that stuff shows up twice. Derivative secant of x is secant of x times tangent of x. The derivative secant of some stuff is going to be secant of the stuff times tangent of the stuff times the derivative of the stuff. And notice I haven't actually taken the derivative of the stuff yet. I just wrote the derivative secant of x cubed over 5 was secant of x cubed over 5 times tangent of x cubed over 5 times the derivative of x cubed over 5. What I want to emphasize here is that for the derivative of x cubed over 5, we don't need the quotient rule. Could you use the quotient rule? Sure. Just like if you were taking the derivative of 5x to the 7th, you could use the product rule. Do you need to? No. The derivative here is just 35x to the 6th. But you could think of it as a product. You'd be like, okay, well, it's the derivative of 5, which is 0, times the other thing, plus 5 times the derivative of the other thing, which gets you 35x to the 6th. So this constant multiple rule, where you just say the derivative of 5 times x to the 7th is just 5 times the derivative of x to the 7th, also applies here. The derivative of x cubed over 5 is really the derivative of 1/5 times x cubed. And the derivative of 1/5 times x cubed is 1/5 times 3x squared. Or as I would probably write it, 3x squared over 5. So the long story short here is that when you have something and you're either multiplying or dividing by a constant, it kind of doesn't matter. If you're multiplying or dividing by a constant, that multiple just kind of does what I like to say, it hangs out. So if you have a function multiplied or divided by a constant, that constant hangs out. For further example, I know I said it, and I keep saying I'm going to move on, but just to kind of make it super duper extra clear, if you have the derivative of, say, like 6 times tangent of x, that's going to be 6 times secant squared of x. If you have the derivative of some gross thing like x to the 7th plus sine of 2x divided by 13, I don't care about that 13. It's not going to really do anything. It's just going to hang out. My derivative is going to be 7x to the 6th plus cosine of 2x times 2 because of the chain rule, all divided by 13. And if you don't like that, I understand. Meaning, like, if you don't like, it seems like I should be using the quotient rule here. The way I get around that is by rewriting it. You can take this alternate path and say, well, I'm going to rewrite this as the derivative of 1/13 times x to the 7th plus sine of 2x. Then it's a little more palatable. You'd be like, oh, that constant multiple is just going to hang out. You can get 1/13 times the derivative of this, which is 7x to the 6th plus cosine of 2x. A lot of people prefer to do it that way.
So when would you like use the quotient rule?
So I'll come back to you, Jordan. Sorry, can you say your question again?
So you said like you circumvented the quotient rule.
Right. So you could use the quotient rule here. I don't want to, but we will. So let's see what happens if we use the quotient rule. So we're going to get the bottom, 13, times the derivative of the top, which is 7x to the 6th plus cosine of 2x times 2, minus the top, x to the 7th plus sine of 2x, times the derivative of the bottom. But the derivative of 13 is what? Right. All divided by 13 squared. And so what ends up happening is you get this divided by 13 squared, and one of the 13s cancels. So we get 13 times 7x to the 6 plus cosine of 2x times 2 all over 13 squared. That 13 cancels one of those 13s, and you get back to the same answer we had before. So you're certainly welcome to use the quotient rule here. It's just, it's using more of a tool than you really need. Good. And I thought, yeah, Jordan, I thought that would answer. So someone asked in the previous problem, don't we need to square the 5 in the bottom? And exactly for the same reason, right? If you were to use the quotient rule to take the derivative of x cubed over 5, you get the same sort of thing. You would get 5 times 3x squared divided by 5 squared, and then one of the 5's cancels. So yes, you can certainly use the rule, but if you're multiplying or dividing by a constant, really dividing by a constant is multiplying by a constant, because really multiplication and division are the same thing. I know it's kind of a weird thing to say, but they really are. Division is just multiplication by the reciprocal. So if I say I'm dividing by 5, you can say, no, you're not, you're multiplying by 1/5. And we both be right. You do need to use the quotient rule if your denominator is more complicated. Welcome, come on in here for Co-16B. Just, may I see your symptom survey when you have a second? So, yeah, of course, yeah, that's exactly what I was. Thank you so much. So, yeah. So I think that's a decent-ish review of the derivative rules from last quarter. You definitely want to make sure those are strong for you, because they're going to continue to be part of your lives for all of this quarter, especially when we start talking about antiderivatives. You need to be able to know how the derivatives work very well to be able to take antiderivatives. So definitely want to make sure you know those trig derivatives. You want to know the power rule, product rule, quotient rule, chain rule. They are all things that are going to continue to be part of our mathematical lives. Well, let us move forward. And how this clock here is killing me. Okay, we end at 10:20, and it is there. Okay, so we got a half hour left. All right, plenty of time to talk about some exponential functions. So, exponential functions. And we'll probably also get the logarithmic functions as well. What do we need to know about them? The first thing I would say is kind of what they look like. So here is a very kind of typical example. F of x equals 2 to the x. Probably my second favorite exponential function. Excuse me. It looks like this. Vaguely. You can certainly graph it using Desmos. It's a great tool to use. Excuse me. If you really wanted to, you could plot some points here. I don't really want you to, though, because you don't need to. You don't need to know a very detailed version of this graph. You need to know a general shape. So what is important to know about this function and its graph? Well, a few things. Its domain is all real numbers. You can put anything in for x and you'll get a result. Obviously, integer numbers are easier to plug in. Like, I know what 2 to the 3rd or 2 to the 4th or 2 to the 5th are. I don't know what 2 to the pi is. I know it's something bigger than 8 and less than 16, but that's kind of it. So irrational numbers as powers get a little more complicated, but that's what calculators are for. The range of this function is everything greater than 0, or all positive numbers. We definitely have a y-intercept of 0, 1. And we have a horizontal asymptote of y equal to 0. A couple other important things worth mentioning, and this actually does come up probably more often than you think it does. is 1. This is an increasing function. And words. There are 2 limits you should be aware of. So the limit as x goes to positive infinity of this function. Well, I mean, we can look at the graph, right? As we go further and further right, the function gets larger and larger and larger. You can also, I think, convince yourself of this without the graph by saying, well, if my power gets bigger and bigger, 2 to a larger number just means you're multiplying more 2's by themselves over and over again. It's going to get bigger and bigger and bigger. The justification is a little, I wouldn't say shakier, but requires a little more insight to see what the limit to negative infinity is without the graph. So with the graph, I think it's really, really straightforward to say, well, as we go to the left, what value is my graph getting closer and closer to? It's looking like 0. Closer and closer, never equal to 0, but closer and closer to 0. But how do we see that? How can you say that 2 to the negative infinity is 0? Or I shouldn't really say that. I should say it's getting closer and closer to 0. Well, here's what I like to do. I like my powers to be positive. If I think about plugging in a very, very large negative number, I have a negative power. So what I would alternatively do is rewrite this as the limit as x goes to negative infinity of 1 divided by 2 to the negative x. Right? When you put something down in the denominator from the numerator, the sign of the power changes. And now look what happens. I have 2 to a very large positive power. I have 2 to the negative infinity, which is 2 to the positive infinity. And I know that 2 to the infinity is very large, and 1 divided by a very large number is very small. So this is like 1 over infinity, which is 0. So that's usually my kind of mental gymnastics I like to do for when I have a power that's negative infinity, is I like to put it in the place where it's not, to make it a positive power. Because then I can be like, oh yeah, positive powers usually make things big. My denominator is big, meaning my fraction is small. These limits do come up kind of semi-frequently, so just something to be aware of. Yeah, we can probably fit this on the same page here. As a contrast, we should look at a function that has a base that is smaller than 1. And believe it or not, that's a 1/3. Hopefully you can kind of see that. Here's the graph of this looks like. You could plot some points. I'm going to mentally plot some points. So I know if I plug in 0 for x, 1/3 to the 0th power is 1. And I know if I plug in 1 for x, 1/3 to the 1 is 1/3. And if x gets larger and larger, my overall values can get smaller. 1/3 squared is 1/9, 1/3 cubed is 1/27, right? Every time I multiply 1/3, my value gets lesser. Still positive, but lesser. So as I go to the right, my values are going to get smaller and smaller and smaller. As I go to the left, they're actually going to get larger and larger. 1/3 to the -1 is the reciprocal of 1/3, which is 3. 1/3 to the -2 is 1 to the -2 over 3 to the -2, which is really 3 squared over 1 squared, which is 9. So as we move further and further left, the values get larger and larger and larger. This function has almost all the same features as the previous one, with a couple exceptions. This is a decreasing function. And the limits to the left and the right are kind of flipped, meaning the limit as x goes to infinity of 1/3 to the x is going to be 0. Because as x gets larger and larger and larger, our denominator is going to get larger and larger. You could also, if you prefer, write this as the limit as x goes to infinity of 1/3 to the x. Now I kind of took a shortcut there. when you have a fraction to a power, both parts get the power. So I really actually probably should have written that it's 1 to the x over 3 to the x. But what's 1 to the x? Or I should say, what's 1 to any power? Just 1. Right? It doesn't matter what power you raise 1 to, 1 squared, 1 cubed, 1 to the billionth power is still just 1. So that's why we're kind of able to ignore the 1 to the x and just call it 1. So then 3 to the x, well, if x is getting very, very large, 3 to the x is getting very, very large, and 1 divided by a very large number is a number that's getting closer and closer to 0. On the other side of things, the limit as x goes to negative infinity of 1/3 to the x, well, graphically, we can see that it's getting infinitely large. But if you don't like that, we could rewrite it as the limit as x goes to minus infinity of 1/3 to the x, and then we could rewrite that as the limit as x goes to minus infinity of 3 to the negative x. Again, I'm doing the thing that I like to do, where I try to make it so I have a positive exponent. Right? If x is going to negative infinity, then I have 3 to the negative infinity. And 3 to the positive infinity is getting infinitely large. And really, well, with the one exception, there's not, I mean, there's a lot to know about exponential functions, but I feel like these are kind of the important things to know. Yeah.
So it's basically negative and positive.
You want to know that if it's a, so here's what I'll say generally. If your function is some base to the x power, you have two different things happening here. You either have your base being greater than 1 or your base being between 0 and 1. We don't consider bases that are negative because they're problematic, and we don't consider bases that are equal to 0 or equal to 1. 1 to any power is boring. It's just 1. It's not really an exponential function. 0 to any power is also problematic. If you have 0 to a negative power, what's 0 to the negative third? It's a trick question. It's undefined. Can't divide by 0. So 0 to the x is a really kind of terrible function. It's undefined when x is negative. In a similar way, so right, f of x equals 0 to the x. It's terrible. We don't do it. For the same sort of reason, a negative base, actually not the same reason, a similar reason, this is also terrible. And I should be maybe more specific. I'm saying terrible when really I should be saying it's problematic because it's undefined some places. We would like our exponential functions to be defined everywhere, to have a domain that is everything. That's not true if you have 0 to the x. You can't have x be negative. It's also not true here. -4 to the x is undefined for certain values of x, like if x was 1/2. What's -4 to the 1/2 power? Well, what's another name for the 1/2 power? And what's the square root of -4? It's not real, right? It's an imaginary number. So we take the square root of -1. And we could definitely say it's 2i. But when you're graphing things, we don't deal with imaginary numbers when we're graphing. So when we talk about graphing functions, there is this implied word that we're graphing real valued functions, meaning the outputs have to be real numbers. And if your outputs are not real, we don't want that. So we don't graph things like this, or we don't deal with exponential functions where the base is negative because they have domains that aren't everything. So our bases should be positive, not 0, and just not 1 because 1's boring. Totally fine. So if your base is larger than 1, it's an increasing function. And the limit as x goes to infinity will be infinity. And the limit as x goes to negative infinity will be 0. Which again, right, if you just think about it, if it's increasing, well, yeah, it's going to infinity that way, and it's going to 0 that. So now I feel like I should be on camera because people can't see me. So let me do the thing. Sorry, I'm doing all these hand things. You guys probably I should try to show you what I'm doing. On the other side, if the function's decreasing, and whenever we say increasing or decreasing, the words that are not said but always implied are from left to right. We are always thinking about graphs from left to right. So if it's decreasing from left to right, then as we go way to the right, meaning to infinity, the function is going to get closer and closer and closer to 0. If we go way to the left, the function is going to get very, very large. These limits come up fairly frequently, so that's why I'm mentioning them. Yeah. So now for the function, for the exponential function that we really care the most about. Can I do something? Let me try one thing here. No, that's not the one I want to do. That one. Let me just try something else out here. Question? Yeah. The answer is complicated. But so the answer is no if your function is specifically number to the x. So like if it's 2 to the x or 3 to the x or 1/2 to the x or any positive number to the x, then no, you can't have a limit be negative infinity because all the graphs have either this shape or this shape. But if we start transforming the graphs, shifting them or reflecting them, then you can have a limit that's negative infinity. So for example, and I know this example is going to look like something I said we can't do. It's not, it just kind of looks like it is. If your function was, say, negative 2 to the x, then things can happen, like having a limit that goes to negative. So I want to point out, actually I should ask, in this function, what's my base? Is it 2 or is it negative 2? It's actually 2. So the negative, so I will say it's not this. So if the parentheses were there, then the base would be negative 2. But since the parentheses aren't, God, that word is not good for me. Since the parentheses are not there, we have to remember the order of operations. So everyone's favorite acronym ever, PEMDAS, right? You know, first you do parentheses, don't have any. Then you do exponents. So this 2 to the x has to kind of happen before you apply the negative. So for example, if I was going to make a table of x values and function values, so when I start plugging in, like if I do 0, okay, well, negative 2 to the 0, I'm doing the 2 to the 0 part first. 2 to the 0 is 1, so I get negative 1. And if I plugged in 1, I get negative 2 to the 1, which is negative 2. If I plugged in 2, I get negative 2 squared, which is negative 4. Right, we're doing the exponent first, the negative part second. So what this negative sign in effect does is it flips the graph across the x-axis vertically. So this graph, instead of looking like this graph, is going to get flipped over this way, like that. So this is going to look like that. And then we can kind of see, well, in fact, we can just use what we had before. If I know that the limit as x goes to infinity of 2 to the x is equal to infinity, right? Because graph of 2 to the x, right? As x goes to infinity, 2 to the x goes to infinity. Well, if I put a negative sign in front of it, I'm really just multiplying the whole thing by -1. If I multiply infinity by -1, I get negative infinity. We can also see it graphically, right? As we go further and further right, this graph goes down, 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 down to negative infinity. So hopefully that's a good answer to your question. Welcome, whoever just showed up. Oh, yeah, okay. So to kind of get to the real meat of this, or kind of the punchline, I suppose, is that the exponential function we typically care the most about, the one we see the most of, is this one. That's everyone's favorite exponential function for a number of reasons. E, which is approximately 2.7. That's really as many decimal places as I think anyone needs to know of it. You could know more. I don't know, like there, yeah, you don't need to know more. It's between 2 and 3, it's closer to 3. But it's a very important number. It's called the natural base. And its graph is, I guess it's special. It's going to look just like all the other graphs I've drawn for these exponential functions because my drawing skills are less than amazing. It looks vaguely like that. It's probably not the best drawing of it. It probably is a little more steep than I've drawn it. I guess one thing that's special about this graph versus any of the other exponential graphs is that at this point, the slope of the tangent line is equal to 1. That might not seem very special, like, well, big deal, but it's the only one, meaning all the other ones, 2 to the x, or 3 to the x, or 5 to the x, they all have tangent lines with a different slope there that's not 1. The reason this is really the important one that we like the most is because of the following. If your function is e to the x, the derivative is also e to the x. That's what makes this function really special, is that it's its own derivative. And there aren't many functions that fit that criteria. In fact, it's kind of the only one. I should be more general here. Technically, if your function is any constant multiple of e to the x, then it's its own derivative. Because of the constant multiple rule, right? Constant multiples just hang out. So the derivative here is c times e to the x. Definitely one to remember. It's going to come up pretty frequently. Trying to think about, let's see, how much time we got? Got 8-ish minutes. Question.
Why is it like a natural base or like
So why is it called the natural base? It's kind of because of this property. So I guess, yeah, it's words. So to kind of go along with this exponential function e to the x, there are also logarithmic functions. So specifically, f of x equal to the natural log of x, which is just a shorthand or abbreviated notation for log base e of x. So this is the natural logarithm. That's what it's called. It's because the base is e, the natural base. The reason we call the natural base is because it's the one that's kind of the nicest. It comes up the most, and it's. Let me give you an example. So I might be getting slightly ahead of myself, but I think you guys will survive. I feel like people really want to come in this room. We still have a few minutes. All right. So if your function is e to the x, I know you can't, like definitely being outside of this room, you can't see him very well. Like I was out here and I was like, oh, I'll do this. How about this? Okay. Now they know. So if your function is e to the x, the derivative is e to the x. If your function is some other non-natural base, the derivative is not as nice. So for example, if your function is 2 to the x, and we will definitely delve into how you get this a little bit later, like probably next Tuesday. The derivative is not quite as nice. It's 2 to the x times the natural log of 2. And more generally, if your function is any positive base to the x power, then the derivative is that base to the x power times the natural log of that base. So that's why e to the x is the natural base, because it's the one that works the nicest when you're doing these things. It also holds up when you talk about logarithms. So even though, so these things are going to come up very fast, so I might as well just say them. So if your function is the natural log of x, again, that just means log base e. It's really just that mathematicians, I was trying to say mathematicians are lazy. They'd rather write 2 letters instead of writing 4. Also, typesetters were trying to save ink. They didn't want to typeset a 4-letter thing when they could have typeset a 2-letter thing. So we're not going to write log base e. That's too many letters for us. We're going to write ln, or natural log. I'm going to say natural log. So I used to work next to someone named Ellen, and I'd be talking about ln. And she'd be like, "Hey, what's up?" And I'm like, "No, I'm talking about math." So I start saying natural log. You can say ln, that's fine, but I will say natural log. The derivative here is 1 over x, which you haven't seen yet. Probably we will definitely talk about, but we don't have time to really talk about it now. So I'm just trying to give you the short, quick of it. And then if your base was something else, so if your function was log base 2 of x, your derivative ends up being, instead of multiplying by natural log of 2, you end up getting the same thing as before, but now you're also dividing by an additional natural log of 2. And generally, if your function is log base b of x, your derivative is 1 over x times the natural log of that base. We will definitely circle back and talk about these on Thursday or Tuesday, but I felt like I should kind of explain why we call it the natural base. You're welcome. In the last couple minutes here, I will just point out a couple graphs. So if I were going to graph, let's give yourself a new page here, James. So just to go along with our exponential graphs, if we were going to graph log base 2 of x, it looks like this. Oops, you might want to see all of that. This is the general logarithmic shape. And what I really want you to know about this at the moment is it's the inverse function of the exponential function 2 to the x. So if I were to graph 2 to the x over here, these two graphs have exactly the opposite xy coordinate pairs, meaning this graph has the point 1, 0, and this graph in red has the point 0, 1. And if I were to plot other points, like say on this graph, I have the point 1, 2, or the point 2, 4. On the logarithmic graph, I have exactly the opposite xy pairs. I really should say the inverse, right? They're the inverse pairs. I have the point 2, 1, and I have the point 4, 2. And there is symmetry here. These graphs are reflections of each other across the line y equals x. And the same is true for any exponential function and logarithmic function that have the same base. So the other example I want to just show you, and then we will be done, is f of x equal to e to the x and g of x equal to the natural log of x. Just a moment.
Oh, I'm sorry, is there class going on?
Yep.
Oh, I'm sorry, everyone was early.
So here's e to the x, which we've seen once. Looks kind of like that. And here is its inverse function, natural log of x. They have a lot of, in fact, if you took all the properties of e to the x, like the asymptotes and the domain and the range and all that kind of stuff, and interchange the x and the y things, you would have all the properties of the natural log of x. We'll talk about that next time, but what I want to leave you with is on your right hand. So look at your right hand. If you're right-handed, which looks like most of you are, set down your pen for a second. Look at your right hand. My hand is not an excellent example of this because I am older and have many lines on my hand. But for you younger people, up here is a pretty good version of e to the x. Down here across like your thumb, if you can kind of see it on my hand, is a pretty good version of natural log of x. So on your right hand, it's gotta be your right hand. On your left hand, they're flipped. You have, what is it? E to the negative x and the natural log of negative x. You don't want that. You want e to the, on your right hand, you have e to the x and natural log of x. So it's kind of a good thing to, like later on today, when you're looking at your right hand, you're like, oh yeah, e to the x, natural log of x. So if you're ever taking a test and you need to know what those graphs look like, set down your pen or pencil, look at your right hand, like, oh yeah, e to the x, natural log of x. Good to go. All right. Nice meeting you all. I will see you all again on Thursday. I'm very available in general, so if you want to come get more help in the non-class time, feel free to find me on all the ways you can. You can, all the info is on Canvas, so take a look in Canvas and find all the things. Also, if you didn't already, please do fill out the attendance form. You can find it on Canvas. You can also find it on this QR code right here. And for those of you on Zoom, it's in the chat. Please fill it out if you haven't already.